Hello, welcome back. In this video we'll discuss the Einstein coefficients and their relations. We have seen what stimulated absorption, spontaneous emission and stimulated emission processes are. While discussing the three quantum processes, we have taken an atomic system where there are two energy levels. One ground state energy level we have represented with E1 and the excited state which we have represented using E2. And the difference of these two states, E2 minus E1, is equal to h nu. But when you have such atoms in very large number, then the three processes, that is the stimulated absorption, spontaneous emission, stimulated emission, they all happen simultaneously. Further, instead of having a single photon, now we'll have a very large number of photons. Using these two conditions of having large number of photons and atoms, we'll obtain the Einstein's coefficients and their relations. In a collection of atoms, all the three processes happen simultaneously. Say we have a system where n1 number of atoms per unit volume with energy E1. Similarly, let us say there are n2 number of atoms per unit volume with energy E2. Say small n is the number of photons per unit volume at frequency nu. Then we write h nu is equal to E2 minus E1, where E1 is the lower energy level or the ground state and E2 is the excited state or the higher energy state. We define a quantity called the energy density. We represent energy density with a rho nu, which is equal to nh nu. Now we'll discuss the upward transition. Say we have the higher energy level E2 and the lower energy level E1. We have the electron in the ground state or the lower energy level. We are supplying, say, energy h nu. The difference between these two also is equal to h nu, E2 minus E1. Under such conditions, when light of frequency nu and energy h nu is incident on a material in which the electron is in the ground state E1, then the electron will absorb the energy and goes to the excited state, that is E2. Thereby the atom becomes atom plus h nu gives rise to an excited atom. This kind of a thing happens when you have a single atom with two energy levels and single photon. Now that we have a very large number of atoms and very large number of photons, we write the stimulated absorption rate. It will be proportional to n1, that is the population of the state E1, and also proportional to the energy density, that is rho nu. We can write this as n1 rho nu times a coefficient or a proportionality constant B12. Here B12 is called Einstein coefficient of stimulated absorption. Now we shall discuss the downward transition. This is the excited state E2 and this is the ground state or lower energy level E1. Say we have the electron in the excited state. For a downward transition to happen, the electron must be in the excited state. Since the electron in the excited state cannot remain forever, it will make a downward transition to the lower energy level. Say tau is the time over which the atom can remain in its excited state, or it can also be stated as the duration over which the electron remains in the E2 energy state or E2 state, and this time period is called as lifetime. The tau is the lifetime. Generally it will be very small, say 10 power minus 15 seconds or 10 power minus 12 seconds. For such a small duration, the electron will reside in the excited state. After the expiry of its lifetime or at the end of its lifetime, the electron would make a downward transition to the energy state E1. When it makes a downward transition, it releases a photon or it releases energy that is equal to h nu, which in turn is equal to E2 minus E1. Such a process is called as spontaneous emission process because the electron is making a downward transition on its own. So the spontaneous emission rate, it will be proportional to N2. So we write spontaneous emission rate as equal to N2 times A21, where A21 is called the Einstein coefficient of spontaneous emission. Suppose you have the electron there and in a time t that is less than tau, that is less than lifetime, if you can force the electron to make a downward transition by means of an external mediation, then you call it as stimulated emission process. In the stimulated emission process, we will be getting the original photon and a photon that is released due to the downward transition. And these two photons will be identical. And that is how the amplification also takes place in the case of lasers. We have one photon initially and this photon is getting multiplied, and now we are getting two photons at the end of the interaction of this photon with the atom that is in the excited state. Such a process is called as stimulated emission process. Now we shall write stimulated emission rate. This will be proportional to N2 and also proportional to rho nu. So we write the stimulated emission rate as N2 rho nu B21. Here the coefficient B21 is called Einstein coefficient of stimulated emission. So we have obtained the three Einstein coefficients: the Einstein coefficient of stimulated absorption, the Einstein coefficient of spontaneous emission, and the third one, that is the Einstein coefficient of stimulated emission. Under thermal equilibrium, the upward and downward transition rates must be equal. Therefore we write N1 rho nu B12 is equal to N2 rho nu B21 plus N2 A21. On the right hand side we are writing the emission processes, and on the left hand side we are writing the absorption process. The label B is used to refer the stimulated processes and label A is used to refer the spontaneous processes. From this one can obtain the energy density rho nu as N2A21 upon N1B12 minus N2B21. Say this is 1. Further, this can be written as rho nu is equal to A21 upon B21 divided by B12 upon B21 N1 upon N2 minus 1. Say this is 2. In this expression, we have a ratio of these two populations, that is N1 upon N2. To obtain the ratio of N1 and N2, we make use of the Boltzmann distribution. The Boltzmann distribution gives us the population of the various energy levels of a system in thermal equilibrium. We use the Boltzmann distribution law. This law states that the population of ith level is equal to Gi N0 exponential minus Ei upon Kt. Here Ni is the population density of the energy level Ei. N0 is the population density of the ground state. Gi is the degeneracy. What is degeneracy? If an energy state is having more than one wave functions, then the state is said to be a degenerate state. K is the Boltzmann constant, and it is equal to 1.38 into 10 power minus 23 joules per Kelvin. The Boltzmann distribution follows this kind of a population distribution. The probability of occupation of E1, let us say it is the ground state, is quite large. In thermal equilibrium in a system of atoms, the higher energy levels population will be small when compared to the ground state or the lower energy level. Using the Boltzmann distribution, we write the population density N1 as G1 N0 exponential minus E1 by KT, and we can write N2 as G2 N0 exponential minus E2 upon KT, and we write the ratio N1 upon N2 as G1 upon G2 exponential E2 minus E1 upon KT, or this can be written as G1 upon G2 exponential h nu by KT. Say this is 3. Substituting the value 3 in 2 will give us the energy density rho nu as A21 by B21 divided by G1 by G2 B12 by B21 exponential h nu by KT minus 1. Say this is 4. We shall compare this energy density with the energy density expression given by Max Planck for the blackbody radiation. The Planck's law of blackbody radiation gives rho nu is equal to 8 pi h nu cube by c cube into 1 over exponential h nu by KT minus 1. Say this is 5. Upon comparing these two, we get G1 by G2 B12 upon B21 is equal to 1, implies G1 B12 is equal to G2 B21, and from the comparison we get A21 upon B21 will be equal to 8 pi h nu cube by c cube. These two relations are known as Einstein relations. In this video we have said that when you have a large number of atoms in a system, then all the three processes they happen simultaneously. We have started our discussion by stating that N1 as the number of atoms per unit volume with energy E1, N2 the number of atoms per unit volume with energy E2, and N number of photons per unit volume at frequency nu. We have obtained the Einstein coefficient of stimulated absorption. In the case of downward transitions, we have obtained the Einstein coefficient of spontaneous emission and the Einstein coefficient of stimulated emission. We have written the energy density expression, and in that we have obtained N1 and N2 using the Boltzmann distribution law. We have said the Boltzmann distribution is given by Ni is equal to Gi N0 exponential minus Ei by KT, after which we have obtained the energy density expression. We have compared the energy density expression with the Planck's law of blackbody radiation and obtained G1 B12 is equal to G2 B21 and A21 by B21 is equal to 8 pi h nu cube upon c cube. These two relations are known as Einstein relations. Thank you.